All right, everybody. Well, welcome back to another session of CE 397, Control Theory for Smart Infrastructure. It's good to see you back. So today is going to be kind of a short lecture. I may give you time at the end of class to work on your homework or projects if we have extra time. I'm not going to go through the full explanation of these concepts because it would take way too long. So I'm just going to show you them and show you how you can apply them through an interactive coding exercise, okay? All right. Well, let's move on then. So last time, in the last two lectures, we covered two related concepts. So we finally got to control of multivariable dynamical systems. We looked at full state feedback control. And here I'm looking at these systems in discrete time because it'll make our lesson today easier. If we have a dynamical system of the form xk plus 1 is equal to axk plus b uk, this is a discrete time LTI system, we can formulate a feedback control law of the form uk is equal to negative k times xk, so a linear function of the current state of the system. And using this feedback control, we can essentially redesign the system however we want. We can create a new closed loop system with poles in the desired locations that we wish, such that we can achieve stability, reference tracking, disturbance rejection, and all those good things. And we also looked at the related problem of observers. This is something we hadn't looked at up until this point in the class, but it's something that's really relevant to a lot of online modeling problems that some of you may be interested in. So we looked at how if we have a dynamical system in standard state space form, we can create a running estimate of the system's internal states by feeding back the difference between the true state, as characterized by measurements, for instance, and our estimated state. So we can feed back the output of the system. So this would be, for instance, sensor measurements. This might be the modeled output. And if we apply this gain term to that difference, we can essentially force the artificial system to track the behavior of the real world system. Okay, and that we called a Leuenberger observer. So that's just a general class of state observers or state estimators that can be used to essentially create real-time estimates from some set of observations along with some model of the system. So we took a look at those two concepts, but there was one question we didn't really address, which was how do we select those gains L and K to get the control and observation behavior that we want? So we kind of looked at this in a heuristic way. I just gave you a set of poles that I wanted you to achieve, but I didn't really give you any justification for why we would want the poles in those places or what even a good selection of poles might be. So we never really looked at the problem of how can we control and estimate the states of these systems optimally. So what we're going to be looking at today are two techniques for optimal control and optimal state estimation. These are very widely used in practice because they're so powerful. In particular, we're going to be looking at two related problems. First, we'll show that the optimal control gain at each time step for this feedback control problem is given by the solution to what's called the linear quadratic regulator problem, or LQR. So this essentially finds the optimal gains for that feedback control at each time step. And I'll show you how to derive that optimization problem. The second problem, which is kind of the dual of the control problem, is the optimal observer problem. And we'll show that the optimal observer gain, LK, at each time step is given by the solution to the linear quadratic estimation problem. And this is often more commonly known as Kalman filtering. This one we will get into a little bit, and I'll show you an example of Kalman filtering, but we're not going to go through the full derivation for either of these because it would take too long. And also I haven't given you the background on stochastic state space systems, which we need to fully understand these two problems. But I want to at least give you some exposure to both of these concepts because they are very widely used. Okay. So again, as I noted, these problems are kind of duals of each other. They are going to be optimal control and optimal estimation problems respectively. And in both cases, we're going to be balancing between competing objectives. So for LQR, we balance between two competing objectives. We're going to balance between deviation from a reference state. So we're trying to track a reference as closely as possible. And we're also going to balance that with control energy input. Okay, so we'll find that there's a trade-off between these two. We can often make a system track a reference really well, but it might take a lot of actuator authority or control energy to do to achieve that task. Okay, so in LQR, we're going to be balancing between tracking a reference and the control energy that we're inputting to the system. For LQE, it's kind of similar. We're going to balance between two other factors. We're balancing between the process uncertainty. Okay, so this would be uncertainty in our model or input. I'll just say uncertainty in our model. And we're going to be balancing that with measurement uncertainty. Okay, so this is uncertainty in our sensor measurements, for instance. So I'll just say uncertainty in sensor measurements. Okay, so in both of these, we're kind of balancing between competing objectives, and we're finding the optimal control and observer gains that balance between these objectives given a set of weights on each objective. That's essentially the concept that we will be using today. Okay, are there any questions on these two concepts? Okay, so let's quickly go through, and I just want to introduce the LQR problem. Okay, so let's say we have an LTI system. This is discrete time. So we'll have, for instance, x at time k plus 1 is equal to a xk plus b uk. And let's say our objective for control, is we want to keep the state x at each time step k as close to 0 as possible. Okay, so in this case, we're essentially, just for simplicity, we're treating our reference as 0. It'll just simplify the math and the presentation of the math. We could, replace this with, keep the difference between x and a reference state as close to 0 as possible. But for now, let's just consider our goal is we want to keep the state x as close to 0 as possible. Okay, and we want to design a control signal which I'll call capital U, which will consist of a collection of control inputs at each time step, U0, U1, U2, and so on, to achieve the following two objectives. First, we want the states to be small. So we want to track 0. We want x0, x1, all the way through the end of our time period to be small. In other words, we want good regulation of the system, good regulation or control. And second, we want to keep our control inputs small. So we want U0, U1, and so on. We want those to be small as well. So small actuator authority. Right. If we have, for instance, a structure that we're trying to control, we may want to eliminate the effect of some disturbance that hits the structure, but we also don't want to use too much power in doing so, right? So we want to minimize both of those objectives at the same time. Okay, are there any questions on this general setup? All right. So we can set this up as an optimization problem. We can set this up. I'll just call this LQR optimization. So we want to minimize both the deviation of our state from zero, and we want to minimize the control energy we're using to do so. So we can express this as an optimization problem. Let's say we want to minimize the sum from time step k equals 0 to time step n minus 1. Let's say so. Let's say we're minimizing over n time steps, and we minimize the following objective function. I will just write it out first. Xk transpose Qx, okay, plus UK transpose R UK plus Xn transpose QF. Sorry, that's not a vector. Xn transpose QF Xn. Okay, and we're selecting U. We're selecting U to minimize this function. So where U is U naught through U n minus 1. Okay, so this is our objective function, and it's a constrained objective function because at each time step, we also have to satisfy our dynamical system. So at each time step, xk plus 1 has to equal axk plus buk. So this is a constrained optimization problem. And let's just go through each of these terms here. So we have that U is equal to U naught, U1 all the way through UN is our vector of control inputs over each time step. We have that Q is what's called the state cost. So I'll say Q is the state cost weighting matrix. So I'll just say state cost matrix. R is the input cost matrix. And QF is the final state cost matrix. So let's go through each of these. So I never defined this in class, but Q and R and QF are all what are called positive definite matrices. Does anyone know what that term means? Has anyone heard the term positive definite matrix before? So a positive definite matrix simply means that if you have a quadratic product like this with that matrix in the middle, that any quadratic product with any vector will be positive. So that means that each of these quantities here will always be positive. So let's think about what each of these terms means. What is this term doing here in our optimization problem? So we're trying to minimize this expression here. What is this term penalizing? Right. So this tries to keep x as close as possible to 0. right? It'll penalize large values of X. So this is the state cost. Penalizes deviations from 0. Okay, what about this term here? Right, so this will penalize large inputs. So let's call this the input cost. And then this term here is just the final state cost. So this penalizes essentially deviations from 0 at the final time step. And it's treated as distinct. Okay, and the LQR problem is to find U, the collection of inputs over each time step that minimizes this problem. So we can write U is equal to argmin of this optimization problem, where at each time step it's constrained by the LTI dynamical system. Okay. Are there any questions on this setup? Any questions on this optimization problem? Okay, so as I mentioned before, LQR is balancing between deviations from our reference state and input energy usage. And in the notes, I have a very long derivation for how one can create, how one can find the optimal solution to this problem. But ultimately, it is given by the following recurrence relation. And you don't have to write this down. It's in the notes, and you can just find it online. But essentially, at each time step, it turns out that the optimal control input is actually given by the following feedback law. Okay, so the optimal control input at each time step, and this is for the generic time varying case where A and B can be time varying. But you have that the optimal feedback is given by this feedback law. Sorry, the optimal control input is given by this feedback law, where we define the gain as follows. And the gain depends on this S matrix, which kind of represents our cost, our kind of weighted cost over time. And that is given by this expression here. And it's a function of both the input cost and the state cost matrix. Okay, so when you have a recurrence relation like this for LQR, this is actually solved backwards in time. So starting with the final time step and going backwards in time. And once you have an expression like this, you can go ahead and code it up, which I have done for you in this notebook here. So let's take a look at this notebook. In this notebook, I have implemented LQR for the 3-story structural system. So just as before, we have our structural system. In this step, I'm actually converting it from a continuous time to a discrete time system. So essentially what I'm doing is I'm picking a time step, and then I'm computing the matrix exponential times that discrete time step, and that will convert the system from from continuous time to discrete time. So I'm converting it to discrete time just so we can use our formulation that I gave you in class. Right. We can compute the homogeneous response for the uncontrolled system, and it should look something like this. And then here I've implemented LQR. So this is the LQR algorithm. Essentially what we do is first, starting at the initial state, we go forward in time and compute those cost matrices going forward in time. And then we go backward in time using that recurrence relation that I gave you. There's two important things to note here. I've defined the state cost matrix and the input cost matrix. And for this particular example, I have that the input cost is about 1,000 times the state cost for this example. And I'm also using a B matrix that gives us a controller on each floor. Okay, so if I run this, I get the following controlled response. So note that the magnitude is now, the magnitude of the displacement is now much smaller. And it has a completely different shape than it did before. It no longer oscillates at all in this case. Okay, so it's the system is no longer underdamped under this control input. Okay, and finally, we can also look at the control input under LQR. So the control input will look something like this. And I've also plotted an animation of the response. So here we have, in the dark color, we have the controlled response, and in the light color, we have the uncontrolled response. So you can see LQR makes the magnitude of the displacement much smaller. Note that in this case, because I've put much more weight on the input cost, the structure can actually be seen to move a little bit under the controlled case. But by changing the relative weights of the input and state cost, you can get it to track zero even more closely. Okay, so what I want you to do just for the next 5 minutes or so is I want you to go through and run this notebook, and I want you to try two things. Just try two things. So run the notebook. And I want you to try changing the relative weights on Q and R. And see what the response looks like. And then second, I want you to investigate different controller placements. So you can define your B matrix differently. And I want you to try to see what's the best, if you only have a single actuator, what's the best floor to put it on. Okay, so I'll give you about 5 or so minutes to investigate those two things. And I just want you to kind of just explore a little bit on your own for the next 5 minutes, okay? So check the effect of relative weights and investigate different controller placements. Okay, cool. Did anyone try changing around the input costs? Okay, so you can see, for instance, if you, let's just make the input costs even greater, so we can have 1 times 10 to the 5th. Let's just see what the result is. So if we make the input cost greater, it'll allow for more deviation from the reference. So we start to get behavior that's more and more displaced, but our inputs are smaller. All right, and so the structure moves a little bit more, but we save a little bit of energy. And if we make the costs equal, we essentially get perfect stillness. The structure barely moves at all, but we use up a lot of control energy. So this is the case where the two cost matrices are the same. You see that the controlled structure just doesn't move at all, essentially. Okay, so that is LQR. I will check on that notebook and I'll see if I can fix those issues. But go ahead and you can use this for your project if you're interested in LQR. It's probably a little late now to use it for your project, but did you have a question, Jimmy?
Yeah, so when you're defining the Q and R, did the magnitude of the cost make any difference, or is it only the relative?
The relative magnitude is what's going to affect the control strategy. But this, basically, when you go to optimize the function, the final value of your optimized function will be different depending on what Q or R is. So in the case of Kalman filtering, that actually has a meaning in that, in Kalman filtering, we're interested in the relative weight given to the sensor versus the model, but it'll still produce an estimated error bound from the Kalman filter, and that's is affected by the magnitude of those weights as well as the relative magnitude. So it does have a meaning in this case in terms of the total cost incurred, essentially. Okay, so let's quickly shift gears now and talk a little bit about Kalman filtering. Unfortunately, I don't have the time to really give these two subjects the justice they deserve. Let's just talk about conceptually what we're doing with Kalman filtering. So essentially the idea is if we have an uncertain model, so if we have an uncertain model of a system and an uncertain measurement of the system, how can we optimally combine these two pieces of information together to get an estimate that's better than the sum of its parts? So if we have an uncertain model and an uncertain measurement of the system, how can we optimally combine these two sources of information together? Okay, so let's say we have just some generic system given by X and T. And let's say we have a modeled output of the system. So maybe our model looks something like this, and it's uncertain. So there might be some uncertainty associated with it. And we also have a sensor observation of the system that might be something like this. So the sensor and the model don't totally add up. This is our sensor. This here is our model. Okay, what Kalman filtering will do is it'll allow us to combine these two estimates together. So we treat the sensor and the model as being two independent probabilistic estimates of the system's true states. And Kalman filtering gives us a way to combine those two estimates together to produce a posterior estimate. So it also allows us to put differential weights on our confidence in the sensor and the model respectively. So for instance, we might have an estimate produced by the Kalman filter like this, okay, that is putting, so let's say this is from Kalman filtering, and this is putting more weight on the sensor. Similarly, we might have an estimate like this that is putting more weight on the model. So it allows us to kind of control our relative confidence in either the sensor or the model. So what we're doing essentially when we're doing Kalman filtering is we're finding an optimal observer gain. So we're finding an optimal observer. So let me quickly just characterize Kalman filtering as an optimal observer. It's going to tie back to our discussion on Leuenberger observers from last time. So let's say we have a state space system. In discrete time, x times k plus 1 is equal to a times xk plus b times uk plus a new vector vk. I'll explain what this is in a second. And we also have a measurement of the system yk is equal to c times xk plus d times uk plus a new vector, which I'll call wk. Okay, so vk, this is a vector that is stochastic. So this is actually a random vector that changes over time. So at each time step, you might think of it as taking on a random realization of values. So this is a vector of what's called process noise. And it essentially represents our uncertainty with regard to the model input, right? So it can be treated as being some uncertainty about BUK, essentially. So you might have an estimate of the input, but you might not know it exactly. And similarly, WK, this is a vector of measurement noise. So if you have a system like a, maybe a vehicle that's traveling, you may not know its position exactly. You may not know its velocity exactly. It may be subject to some sensor error, right? Or any of the systems that we've talked about in class, whether it's a circuit, the structural system's position, all of those would be measured by something like a sensor, like an accelerometer for the structure, which is going to have some uncertainty or noise associated with it. And we can treat that as a random vector of measurement noise. And for the Kalman filter, we're going to assume that both of them are Gaussian. So both are going to be vectors of Gaussian noise with zero mean and a covariance given by this matrix WK, VK for the process noise. And for the measurement noise, it's also Gaussian with zero mean, covariance WK. So unfortunately, I don't have time to go through the definitions for these, but you can treat essentially those vectors as being vectors of noise as having a mean of zero, but with some standard deviation or some error associated with them. Okay, so let's tie this. Oh, yes? Yes. So you will, for the Kalman filter, you'll need to know the relative difference in the standard deviation between the two. So you'll need an idea of which you're more certain in. So like with LQR, it's the relative difference between the two costs that matters. In this case, it's the relative difference between the two sources of noise that matters. But yes, you will need some characterization of the standard deviation or the variance of those noise sources. Good question. Okay, so let's talk a little bit about the Kalman filter, thinking about our discussion of observers from last time. So we showed that for a state space system of the form x, x is equal to ax plus bu, we could create an artificial running estimate of that system using an observer where we fed back the difference between the true observed output of the system and our estimated output. So we have that x hat k plus 1 is equal to ax hat k plus buk plus L, and I'm going to say L at time k plus 1 times y k plus 1 minus y hat k plus 1. Okay, so this is just our Leuenberger observer from last time, and then y hat k is equal to cx hat k plus du. Okay. Okay, so we specified this observer, but just like with the control problem, we didn't specify how to select the gains for our observer L, right? So what we can do is we can specify an optimization problem just like we did for LQR for this observer problem. Okay, specifically, first, from this system, we can express the error dynamics. Remember that the error is equal to x minus x hat. And if we plug that in and simplify, what we get is the following. So we have, for x, we have axk plus buk plus vk, our vector of random noise now. And this will subtract our expression for x hat k, which will be ax hat k plus buk plus L times k plus 1, yk plus 1 minus y hat k plus 1. Okay, and eventually, if we take this and we simplify it out even further, we get the following expression for the error dynamics in discrete time. E at time k plus 1 is equal to a minus lk plus 1 c times ek plus vk. So this is now adding a vector of random noise plus LK plus 1 times W K plus 1. So this is our expression for the error. And as I mentioned, with the Kalman filter, what we're going to do is we're going to try to minimize this error. Now you'll see there in selecting L, we actually have a conflicting objective now. Can anyone see what it is? So remember that V was our process noise. W was our measurement noise. And selecting L, we're trying to select the poles that essentially make the error dynamics decay to 0, right? So we want this closed loop matrix to have highly negative eigenvalues, right? We want that error to decay to 0. But what's going to happen if we make L very large? Think about this term here. Yeah, so that we're going to blow up the measurement error, right? So in selecting L, we have to balance between these two objectives, just like for LQR, we had to balance between the state and input costs. So what we're going to end up doing is we're going to set up an optimization problem to minimize the mean squared error. So for Kalman filtering or for LQE, we can set up the following optimization function. Right, so we are going to minimize the sum from k equals 0 to n of the expected value of EK transpose EK. So because the error is stochastic now, because we're adding in random vectors, we can no longer just evaluate this deterministically. We have to look at the expected value of the mean squared error. So this expression here, this is the mean squared error. Actually, I should put a 1 over n out front. Sorry, 1 over n for the dimension. So this is equal to, the sum of x minus x hat squared, essentially. So this would actually be, let's call this j equals 1 through n for the dimension of x. So this is the mean squared error. Okay, so Kalman filtering, we are trying to minimize that mean squared error, subject to we have to have that our error dynamics are satisfied. So we have from the previous slide, our equation for the error dynamics. At each time step, we have to satisfy EK plus 1 is equal to A minus LK plus 1 C EK plus VK plus LK plus 1 times WK plus 1. Okay, so this is the Kalman filtering optimization problem. And just like with LQR, there is a closed form solution for this problem. And it takes the form of a recurrence relation just like before. Okay, so we have that the optimal observer is given by the following expression at each time step. You don't have to write this down. It's coded up for you in the notebook, so you can take a look at the notebook if you're interested. But the optimal observer is given by this observer here, where LK is defined using the following matrix expression, using this P matrix that evolves over time. So P is what's called the error estimation covariance matrix, and it essentially expresses the error over each time step. Okay, so as I mentioned before, you can use this error covariance matrix to essentially establish the uncertainty bounds for your estimates, for your posterior estimates of the system state. Okay, so let's go ahead and apply this. So I've created another notebook. Let's say, okay, so I have a structure. So you can go ahead and open up the notebook LQE structure. Okay, so just like before, I created our 3-story structural system and simulate the homogeneous response. And here I'm defining some parameters that we need for our Kalman filter. So first, I'm specifying the observation matrix. So I'm saying that we can only observe the middle floor. So if you have our full observation matrix is C full, I'm selecting just the middle floor. Okay, so we can only observe the middle floor. I've set the process noise standard deviation to 1 × 10⁻², and I've set the measurement noise to be equal 1 × 10⁻². Here I'm generating some observations of the structure's movement. So this is observations of the ground truth movement of the structure that we're going to use for our sensor data. And you can see this is our observation of the structure's movement. You can also use these parameters here to turn on noise. So you can also add random noise to the structure if you want. So here I'm just going to turn on some random noise, and you can see it adds that to the structure, to the sensor observations. But for right now, I'm just going to leave it 0. Okay, so we're going to go ahead and run the Kalman filter. It's going to run that recurrence relation. So just as I specified in the slide. And here we have our true states in the solid lines and our estimated states in the dotted lines. So you can see that it tracks the middle floor almost perfectly. For the other 2 floors, it's a little bit off just because it can't observe those floors directly, but it's reconstructing their states as best as it can. All right, and I've just also plotted a little animation here. Here we have the true structure in the darker color and the Kalman filtered estimate in the lighter color. So you can see that it tracks the middle floor really well. The other ones, it takes a little bit of time to catch up. Okay, so what I want you to do for the next 5 or so minutes is I want you to just explore this code. So what I want you to try is the following. And you can work in groups for this. So first, try modifying the relative weights of the measurement and process noise and see how it affects the results. So you're going to change those standard deviations. Try adding the process and measurement noise to the system. So you can use those Boolean valued functions to actually add noise to the input and add noise to the sensor measurement. And third, I want you to try to find the best sensor placement if you only have one sensor. So find which floor gives the best estimate if you have a sensor only on that floor. One quick note I wanted to make, it may not have been apparent just from how quickly I showed these slides, but if you look at the LQE recursion and the LQR recursion, they're almost the same. It's just the matrices inside of them are switched around. So you'll actually see if you go through for LQR, the equations are the same, except in LQE problem, A is exchanged for A transpose, B is exchanged for C transpose, K is exchanged for L transpose. The cost matrix in LQR, S is exchanged for the process, for the error covariance matrix P, and the input and state costs are dual with the measurement and process noise. Okay, so just an interesting duality between the two. All right, so I'll give you 5 minutes or so to take a look at these problems. This doesn't need to be turned in. I just want you to explore a little bit with this code that I gave you. And yeah, I'll answer any questions or check on you as need be. Okay. Did anyone find what they think is the best controller placement? I'm gonna go ahead and try. Let's see.
It's like the second.
Second floor. Let me evaluate it here. All right, so the first floor gives us a total squared error of 196. Second floor. Oh wait, I'm sorry, I'm overwriting. Okay. What do we here? Okay. All right, first floor gives us squared error of 345. Second floor is 196. Third floor is 178. So actually third floor is the best. Interesting. Okay, so with that, I don't have any more I want to show you today, so I'll give you the last 15 minutes. You can take off early if you want, or you can stay around and do homework 7, because I know many of you are stressed about getting homework and projects and done and stuff. And you can also use this time to ask me any questions you want, and I'll just be over here. And then I'll also have office hours at 5 if you want to talk